Hey guys, so this is our submission for the 2025 UNC Quantum Hacks Hackathon. Basically what we did was we made a probabilistic Sudoku solver. So it's a traditional 9x9 Sudoku grid, the same rules, so you can't have repeats in the same column, you can't have repeats in the same row, and you can't have repeats in the 3x3 squares. And what we did was we created a solver to help solve difficult Sudokus. So I'll basically run through the code. Well, um, we have the JavaScript to do the front end. This is the Sudoku game logic. We want to make sure that the board is consistent, so if there are duplicates and the user inputs like an invalid Sudoku board, then it's going to return an error. Um, we have scraped sample Sudoku boards. Make sure that the random Sudoku is valid, and then we're going to only give the user some of the squares. Okay. Difficulty on the lower right. If you look at the board, so this is an easy board, so a lot of numbers are given to you. The numbers that are given to you are the ones that are in the black cells, sorry, the black text, and only one digit in the cell. Then empty spaces are the white spaces. So this is our solver. If you look at the empty cells, the digits in those cells are the possible digits, right? For some of those cells, it's only one digit, which means that you basically know what the digit is. But for some of them, there's like a range of digits. For instance, if you look at the left middle region of cells, right, some of those have like 1, 4, 8. So those cells could represent a variety of values. This is an easy board, so the digit placement is basically pretty fixed. So what we did was we implemented a probabilistic solver. What that means is for each empty cell, we shade in the digits relative to how likely they are to be the thing. And we allow users to select multiple digits per cell as a guess. Right? In traditional Sudoku, you can only select one per cell, and your goal is to find the optimal or the correct configuration. But sometimes you can't narrow it down to just one. So what we've done is we've represented each cell as a linear combination, of digits. So you can think of the digits as ket, so ket1, ket1, ket2, ket3, all the way to 9. And then the coefficients for each ket are the probabilities. And all of these cells, based on their configuration, are entangled with each other. So let's say I select, for one of my guesses, I can select multiple numbers. That's our improvement. And when you do that, we collapse the weight functions of the entangled cells for that digit respectively, right? So if I select, let's say I only select one digit per cell. So I select like 2 in one cell. That's going to collapse the weight of 2 in all of the corresponding column cells and row cells and the 3x3 square cells to 0, right? But let's say I can't narrow it down to just one digit. So I select maybe 1 and 4. That's going to collapse the wave function by a factor of n minus 1 over n in the corresponding column, row, and square. And basically, the user can look at how green the digit is as a function of how likely it is. And so we've normalized the weights for each cell, and then we display it based on hue. So the lower the probability of the digit being in that cell, the more less shaded it will be, so the more white. And then the higher the probability, the more green and darker the shade. Yeah, so that's our how many cells you get originally. You can assign selected numbers. So this is our UI. that's our submission. Thank you very much. We had a great time doing this, and we learned a lot.